Alright guys, so today we'll be talking about shear stresses in bending. We have already in the previous lectures have seen what do you mean by bending stresses, what do you mean by normal stresses, what do you mean by bending in let's say X plane, Y plane, or what do you mean by pure bending, what do you mean by asymmetric bending. So we are trying to go to the next step. For all the basics in bending, you can refer previous lectures. Today I'll be focusing majorly on shear stresses in bending in different cross sections. So for thin walled sections, we'll be talking about shear flow and shear center. That will be a separate lecture itself. So today we'll be talking about mostly thick walled sections like I section, C section, and maybe rectangular, circular, and all these things. So it is very basic. But few formulation we need to take care of. So I'll be deriving few things, then we'll try to solve some numericals. Exam numericals, we'll try to create a separate lecture for it. Alright, so we'll begin with shear stresses in bending. Alright, so when we say shear stresses in bending, and keep this in mind, this is very important part in bending, because we'll be talking about shear stresses which are present in torsion. We'll be talking about shear stresses under only the load which is parallel to the surface. We'll talk about all this. So I'll give you a very simple example so that you can visualize all these things. So let's say you have a cantilever beam on which a load acting, let's say, is P. All of us have seen this type of beam. I'll give you an explanation of this in more detail. And let's say the cross section of this beam is, let's say, rectangular, or let's say circular, or let's say I section. For time being, I'm assuming it is thick walled, and so. Similarly, we can have, let's say, simply supported beam carrying a load P here, or maybe uniformly distributed load. This is point A, this is point B with some cross section and so. So what do you mean by shear stresses? It's simple as that. So when you have a beam, let's say this is a cantilever beam. Cantilever means I'm fixing it from this end. So this is what you're observing is length of the beam. Alright, once you have length of the beam, if you go to this side, or I change the view for you people, you will observe the cross section. So let's say this cross section is rectangle. I hope view is clear. So throughout our section, right, I'll be talking about our cross section is maybe, let's say, X and Y. It can be Y, Z, that depends upon coordinate system formulation. Whatever you want, it's fine. Similarly, you have a simply supported beam. So I'm simply supporting this beam on both the ends. You're applying a load or maybe a UDL. And if you see from this side, again, you're going to see a cross section of this. I hope visualization is clear, how a beam looks like and what do you mean by cross section of a beam. Now think about this. You have a beam, you have fixed it here, and now you are applying a point load at this end. Alright, so this is what the diagram I have drawn. I am just showing you the replicate case. So if you change the view, what you observe is there is a rectangular section and through which load is passing. If you observe, it is passing parallelly to it. Alright, so any load which is acting parallel to the cross section. So there are two ways. Load can be perpendicular to the cross section. Load can be parallel to the cross section. It can be this, it can be this. So parallelly I'm interested in. Then we'll say these loads are shear loads. And when we say any shear load acting on the system is, let's say, P. Alright. And this cross section area is A. This area is A, then shear stress tau on this face will be given as force divided by area. We all have seen this basic formulation of calculating stresses. Stress is nothing but force divided by area. So if you have a system in which you are pulling your system like this, so force by area will give you a normal stress. If your force itself is parallel, divide by area will give you a shear stress. So assuming that you understood what do you mean by shear stresses. Now why we name it as shear stresses in bending? The reason being, once you have a system which is fixed here and you apply a load which is parallel to cross section, that means shear force. So this will automatically try to bend your structure. So it can be any case of bending. So shear loads, these are also known as transverse loads. When you apply on a beam, it will try to bend your beam. When these type of loads acts on a beam, what type of stresses act on the system are known as shear stresses, and we should know how to calculate the what are the formulas for this, how to compute the shear stresses in any given cross section. I hope you understand the meaning of this heading, which is known as shear stresses in bending. Shear means load acting parallel to the cross section. It will create bending in your whole system, and we are just calculating stresses. If you recall, the basics of strength of material says any force acting on any cross section is nothing but force divided by area. So there is the basic formulation. Then we are trying to do this something else in bending. We'll see whether the formula comes out to be same or is it somewhat different. That's what the main motive is. So what we'll try to do this today is, in shear stresses we'll be talking about different cross sections. So I'll go for rectangular cross section, then we'll go for circular cross section, and then I'll give you a formula which is generalized for any type of cross section. Let it be I section, Z section, C section, any cross section, you can apply that formula directly and you will end up with the formula of shear stresses. Keep one thing in mind. Okay guys, if I'm going a bit fast, or if you're not understanding anything, you can just go back to the video and try to understand why we are talking about shear stresses in bending and what is the main motive of doing this. So you have a separate lecture of calculating shear force and of drawing shear force in bending moment diagram, which is kind of, once you know the shear force, then only you can calculate what? Shear stress. So I'm not going into that, assuming that you know what do you mean by shear force and what do you mean by shear force diagram. So let's start with the basic formulation of first cross section. So I'll remove all these basics part and I'll go to the first derivation. So you can give your heading as first one, shear stresses in rectangular cross sections. Alright, so I'll give the heading as rectangular cross section. So I'll try to derive it now so that you have complete understanding, and then we're going to give you, I'll give you a formula which doesn't need any derivation. You can directly solve a numerical which comes in your exam by that shortcut method. Alright, so I'll go for the derivation now. So let's say you have a rectangular section. I hope everyone understood this now. What do you mean by section? It is what you will see from side view of a beam. So if this is your beam, this is what you're going to observe. So you're observing circle, the circular cross section. For time being, I'm assuming that there is a beam with rectangular cross section. So cross section is what you see from side view. And I'm assuming some coordinate system. Let's say this coordinate is x and this coordinate is y. Alright, now I want you to look for the derivation. So derivation is tau. Alright, and because your cross section, those who have done, those who have already gone through the basic elasticity lecture will come to know this xy plane is basically nothing but your z plane. So this is x, this is y. So this is basically your z axis. So how the formulation or the notation of shear stresses goes: first suffix tells you the plane on which you are acting, and second tells you in which direction you will go. So either it will be tau zx or it will be tau zy. Those who, if you have doubt in this naming convention, why zx and zy, you can directly go to basic elasticity lecture and see sign convention of a 3D stress tensor. You will come to know like what do you mean by first suffix and what do you mean by second suffix. Alright, and the formula I want you to remember is S divided by IB, and then basically the formula is A into Y. This is the generalized formula which will never fail. I am going to use this for rectangle, I will be using this for circular, I will be using this for any arbitrary cross section. So easier to remember, SAY, say, divided by I into B. We will see the meaning of each term. So S is the shear force acting on this cross section, which I told you, P load acting here. It can be anything, it can be P by 2, P by 4. How to calculate shear force is to be properly covered in shear force diagram lecture. So let's say you have a shear force acting of 10 kilonewton, 20 kilonewton on this. We'll talk about in great detail about this A and Y. This is the major thing we need to understand. I is bending inertia. So if you're bending about x-axis, this will be IXX. It is bending about y-axis, it will be IYY. And B is the thickness where you want to calculate your shear stresses. So we'll talk about this. I'll do a simple derivation. and please try to get this, because this is the main essence of shear stresses. So I'm not going to give any suffix. I hope you understand that we are calculating tau. So I'll go to this cross section and I want you to understand this. Alright, so I'll remove this hashed line so that it's easy to visualize few things for you. Alright, now what you'll do is, in this rectangular section, I'm saying this width is B and this whole depth is H, because this is origin. So this is plus H by 2 and this is minus H by 2. I hope this is clear to everyone. So from origin, I'm moving down at a distance of y1 and I'm considering a horizontal strip here of thickness dy. Guys, again I'm saying you can skip this derivation, but this will make you understand, make you more comfortable with the topic. So we'll be doing this for rectangle, maybe we'll do this for circle, and then I'll try to give you a formula that you can skip everything, all the formulas which I'll be deriving, and you can directly go to this and solve any numerical. Not only rectangular, you can solve I section, C section, Z section, whatever aircraft beams, cross sections you can use this formula to calculate shear stresses. Alright, so I'm again repeating this. I've considered a small thin strip of width B, thickness dy at a distance of y1 from origin. This whole rectangle depth is H and width is B. XY coordinate system is present. Alright, now I'll write few terms in this. S is the load divided by I is the moment of inertia and B is the thickness. We'll come to IB, how to calculate these quantities. S divided by IB comes into picture. Now there's a major part. I'm starting an integration sign. The reason of integration sign is because I've considered a small strip, right? I need to consider this whole rectangular zone. So what I need to do is I need to integrate it from one point to another point to cover the whole area. Alright, that is the reason integration comes into picture. Don't have any fear for this. This is simple, straightforward. Now y I'll keep as it is. What is y present here? Now area for this strip I'm interested in. I hope it is clear to everyone. Area of this strip is B into dy. Alright, so you have y, area of this strip is B into dy, and we are moving from point, we have already reached y1, and from here I want to go to the outer end. Alright, so just check for the limits. I'm starting from y1, alright, and I'm going to h by 2. Now you can have doubt why we are saying y1 to minus h by 2 or y1 to. So this strip can be imagined upward, downward, anywhere. You can, if you want, you can keep there as minus h by 2. Doesn't change your solution. You will come to know in a bit why. The reason being, when you're integrating y with respect to dy, it becomes y square by 2. So when you substitute upper limit, either it is h square by 2 or it is minus h square by 2. It's one and the same thing because you're squaring the quantity. So I'm again repeating this. S copy pasted, IB copy pasted, Y copy pasted, and area is represented as B into dy from this strip, and I'm moving this strip from this point till the end. We will see why we are moving from this point to this end. That we'll just going to see in a bit. So what I'll do is S divided by I into B. From this integration I'll pull B outside. Integration y1 h by 2, and we have y dy. So this B and this B got cancelled out. When you integrate y, it becomes y square by 2, and I'll substitute the limits. So I'm skipping those steps and I'll writing it. This S divided by I by 2. So 2 comes outside. Inside you have y now, and it becomes h by 2 whole square minus y1 square. So your shear stress comes out to be S divided by 2I h by 2 whole square minus y1 square. I hope this is clear to everyone. There is no hidden concept, there is no catch involved in this. What you need to do is you just need to remember this formula. Say divided by IB. SAY divided by IB. Again, you should not do anything in this in your GATE exam. This formula and maybe the result I'll be deriving is one and the same thing. So if you have any doubt, please repeat this. Be very comfortable with this. What is y1? y1 is nothing but the distance at which you have considered your strip. So don't bother about it. It won't matter much. I'll tell you why it is important part for us. Now I want you to do this. Please move this strip and reach here. Can you tell me what is y1 then? y1 will be 0. Correct, right? So when you substitute y1 0 here, this will be s by 2i h by 2 whole square. This term will go to 0. So you have some stresses. Can I say when y1 is 0, you have the maximum stresses? So when y1 goes to 0, you have maximum stresses, and you have seen this in previous that this is nothing but your neutral axis. Your centroidal axis is also your neutral axis. So we have maximum shear stresses at neutral axis. Now, second thing, we write this. Substitute y1 as h by 2. Let's say you have your strip on the top. So when you substitute h by 2, this becomes h by 2 whole square, h by 2 whole square, this goes to 0. Similarly, you can substitute minus h by 2, again it becomes 0. What do you mean by this? Shear stresses in bending is maximum at neutral axis and 0 at the outer fibers. If you recall, when we talked about normal stresses in bending, right? Shear stresses, normal stresses in bending was 0 at neutral axis and maximum at the outer fibers. This is the major difference. Exactly opposite thing is happening in shear stresses. It is 0 at the outer fibers and maximum at the neutral axis. So this is a very important point, asked many times in your GATE exam with different cross sections, theory, and we have separate separate lecture for exam numericals. So we'll come to that. So I'll formulate what I'll do. I'll say at y1 equals to plus minus h by 2, we got tau as 0. So there are no shear stresses present when you have when you are at the outer fibers. Similarly, when we have y1 is equals to, if your y1 is equals to 0, if you observe, you are getting tau max as, now we substitute this, s divided by 2i into h square by 4. Just substituted y1 as 0. I hope it is clear to everyone, and I'll try to move forward. I'll remove this. If you have not copied down this, please go back into the video and please copy this. So I'm coming to the major part. Alright, so you have already derived this. From this condition you have derived these two. Now what I'm going to do is I'm going to enhance this tau max. So I need your help in this. Try to get this s divided by 2. I want you to tell me what is I for a rectangular cross section. So everyone knows this B, because we are talking about, guys, we are talking about IXX for time being. This is bending in vertical plane. So B, basically we learn the formula dB cube, but in this we have H. So I'll substitute the formula B H cube by 12 substituted, and you have what? H square by 4. Alright, now let's cancel out few terms. This and this got cancelled out, this and this got cancelled out, one h square got cancelled out. So what is tau max now? Take this 3 2 up, so it becomes 3 by 2 s divided by b into h. Can you tell me what is b into h for this rectangular section? Area, right? So it becomes s by area. S is nothing but the force acting on the cross section, shear force. Force divided by area is nothing but what? Shear stresses we have seen from our childhood. Force divided by area is shear stress, force divided by shear area is nothing but shear stress. But what we are getting now, that actually our maximum stress is 3 by 2 times of what we have learned till now. What do you mean by 3 by 2? 1.5. 1.5 means 50% higher than what we were predicting till now. So this is what we have done with this derivation. You have removed the error. So what we have learning up till now, right? Force by area, force by area, force by area are nothing but the average stresses acting on the system. Now average is not a good thing. It's good for an initial statement, but if you want to be very precise, you need to calculate those quantities. So maximum, I am saying, comes out to be what? 3 by 2 of tau average acting on this cross section. Average is always force by area. But actually our formulation is 50% higher than average quantity. Alright, now I hope this is clear to everyone. Alright, now what I'll do is, tell me what is, this is happening at what location? This is happening at neutral axis. What is stress at the outer fibers? 0. Now let's draw the distribution for this. So distribution goes how shear stresses vary along the cross section. So this is your neutral axis. Alright, this is your neutral axis. And if you move along the cross section, what is shear stress here? What is shear stress here? What is shear stress here? We know shear stress here and here is 0, and at the center it is 3 by 2 times of tau average. What is the formula of calculating tau average? Simple force by area, that is S divided by B into H. Alright, so let's draw the distribution. So at the center, you are saying we have huge amount of stress. And at the outer fibers, you are saying it is 0. So at this point it is 0, at this point you have a huge amount of stress. Now, I want to join this envelope. Now this is the reason I have not removed this from starting derivation. Shear stresses in cross section varies as square terms. Now what do you mean by square terms? These are parabolic variations. Bending stresses, which are known as normal stresses in bending, are linear variations. If you recall, your formula was, for normal stresses, your formula was m by I into y. Correct, right? So there is only y to the power 1. So this is linear. Normal stresses are linear in cross section. Shear stresses are parabolic in cross section. So if you want to draw this right, you should draw this envelope like this. It's kind of a parabola. What is the center value? This is tau max. What is this? 0. What is this? 0. This is how shear stresses actually vary in bending numerical. What we were doing till now? Everywhere in cross section, your stresses are same. And what is that magnitude? Tau average. Now I hope you understand what we were doing before and what we are doing now. Before we were saying tau average at the outer fiber is force by area, at the center it is force by area, at the lower fiber it is force by area. But now what we are getting, actually at our outer fibers there are no shear stresses. And at the neutral axis the formula is not force by area, it is 50% higher. So if your average shear stress comes out to be, let's say for example 100 MPa. So at center actually it is not 100 MPa, it is 150 MPa. So this is the error you have introduced because of your approximation. Now initially we were saying it is 100 MPa here also, but actually what stress acts here? 0. I hope you understood this part. So when you have a rectangular cross section from now on, if someone asks you what is the maximum shear stress acting on the system, you need not to do any of this formulation. Maximum is nothing but 3 by 2 times of tau average. How to calculate tau average? Simple force by area. So you have a rectangular cross section, 10 kilonewton force is acting on it. So let's say, just for an example sake, I'm saying you have a rectangular cross section of width 10 by let's say 5. Alright. And a shear force of 10 kilonewton is acting on it. And if someone asks, tell me what is tau max, or tell me what is tau at the outer fibers, we know 0. What is tau max? We know it is at neutral axis. So now no need to do any of these formulation. This nothing is required. What you directly say is 3 by 2 into tau average. What is tau average? S divided by area. So what is S in our case? 10 into 10 to the power 3 divided by area is what? 10 into 5, let's say this is in mm. Solve this, you will get what? Tau max acting on this rectangular cross section. But keep one thing in mind, 3 by 2 into tau average can only be done for calculating tau max. If in any between quantity, let's say they'll ask, tell me what is stress here, tell me what is stress here, what is stress here, you cannot use this formula. It will give you the maximum value, and we know maximum value is at the center. So there are two ways of asking this in your exams. What is the maximum value of shear stress acting in the cross section? Or what is the value of shear stress acting at neutral axis? Both are one and the same thing. Any other location apart from this, either you can learn this formula, substitute that, or I will give you a very simple, sweet shortcut which will directly give you the values. So let's come to that afterwards. But let's summarize what we have understood. In rectangular cross sections, average shear stress is given by force by area. But actually shear stresses are different, which is given by this formula. And if we go by this formula, we came to know few important points. Shear stresses are maximum at neutral axis and 0 at the outer fibers. Maximum value of shear stress in rectangular cross section is 50% higher than tau average value. And next point is shear stresses in bending varies parabolically along the cross section. So if you see the cross section, the shear stress actually varies in the parabolical direction. So these are the points you should remember. We'll summarize by the end of the lecture how much things you need to remember and how much things are more than enough to solve the numericals. Alright, so moving on to the next cross section, which is known as circular cross section. Alright, to give you a heading as circular cross section, I'll remove all this. We can do the same derivation, or we can skip this and go for the, but I'll give you the derivation because it is kind of an important result for circular cross sections also. Most of the times we have shafts which are more, all the shafts are circular, right? So it's better to cover that particular topic also. Alright, now from rectangular section, excuse me, I'll go to circular. When we say section, it is clear to everyone, it is cross section. Alright, now what I'll do is, I'll draw a circular cross section which is solid, and again I'm saying this is X, this is Y, so you're calculating shear stresses using the same formula. Now I'll go to that formula. See, if you're saying tau, the formula which we should remember is SAY divided by IB, right? Now I'll try to get this thing alone. What is this? No, if I go in, zoom in this quantity, right? This is nothing but area multiplied by some distance. So this is known as moment area. Alright, so you have an area and you are taking a moment about it, so it becomes moment of an area. So for time being, I am only calculating that moment area, and maybe it is more clear. Again, I am repeating this. You can happily skip all the derivations. The only thing you need to understand is the why we are doing this and what are the final results we are getting. So when we say moment area, again I am saying area of that small strip multiplied by some distance. So I want you to tell me this now. Let's say in circle, now in circle the issue will start. The reason being, in rectangle this width was of thickness B everywhere. Now this is different, correct, right? Now what we'll do is this. Let's say this circle is of radius R, alright? At a distance y1, we have assumed a strip of some thickness. Now of thickness dy and some length. Now I want you to tell me this length. How will you calculate this? Because area, if you recall, right, was y into dA. That's what we are trying to do. So y is the distance. If you recall, in place of dA, I have substituted, in place of dA, I have substituted b into dy. Correct, right? But now the issue is there is no b here. There will be something else. Now I want you to tell me this. Y, alright? Tell me this area, guys. D area. So I want this length. Think about this. This radius is r square. This is y1 square. So I'm just taking, applying Pythagoras theorem and writing this as r square minus y square at a distance of y1. Alright, so I'll be integrating this again. So I'll write this as r square minus y square under root. Half portion is considered. Why not I'm not writing y1? The reason being, I'll be integrating this. Correct, right? Integration from what? I'll be integrating from y1 and I'll go till the end, that is r. Now y is already present. We are breaking down this area term. Area is nothing but this whole length multiplied by dy. Now this length is r square minus y square. This is multiplied by 2 into dy. So maybe it is slightly confusing, but go very slow step by step. I just want this strip area. So I've calculated this thickness multiplied by 2 multiplied by dy. 2 r square minus y square under root into dy is the area. Multiplied by sum is nothing but the moment of area. So moment area I have written. This is basically a y quantity. Then we'll multiply this with s divided by I divided by b. We're going to get the same formulation what we have done for rectangular section. Now I'm skipping few integration part, but maybe you will understand this. Derivative of this y square is already present outside, which is 2y. 2 into dy. Correct, right? Now we need a negative sign. So if you integrate this, right, this integration will be directly straightforward. See, in differentiation of y square is 2y dy. Correct, right? With a negative sign. Now negative sign is not present, so I'll apply a negative sign. And if you integrate this, this is r square minus y square to the power 1 by 2. So this becomes r square minus y square to the power 3 by 2 divided by 3 by 2. And keep this in mind, you are integrating this between the limit y1 to r. Now, slow. If you have not understood this step, just do substitution. Put r square minus y square is equals to t. When you put r square minus y square is equals to t, derivative of this will be 2y dy, which is equals to dt. And then you do the substitution, come back, you will end up with this formula. So assuming that you can do this, if you have doubt, please ping me in the comment section or ask in the doubt clearing group, or WhatsApp me or any other person added in the group, any other faculties. But this should be clear. Now Go slow and tell me about this. When you substitute this r square term here, r square minus r square, this upper limit will go to 0. You already have a negative sign. With lower limit you have a negative sign, so it converts positive. This 3 by 2 goes up, so it becomes 2 by 3. And I am substituting y1, so this becomes r square minus y1 square to the power 3 by 2. So this is what we have derived is only ay portion. Now I will be multiplying these things to it. Alright, let's do this. So keep this in mind. Now I'll substitute those quantities here. Alright, so S divided by I, I'm not touching this for time being. Now B is, what is the thickness where you are? What is the location? So thickness we know, r square minus y1 square under root multiplied by 2. So I'll write that term here, 2 r square minus y1 square under root. Guys, please don't have this doubt that I have used y1 here and I have used y when I have done this derivation. When you are inside an integration sign, you cannot be specific. You cannot be at y1 location. You need to be in terms of parameters like x and y. When you are at a particular location, you can substitute y1. Here, we are not integrating anything. In this, we were integrating terms. Now, this I, B is nothing but this here. Ay is this. So if I substitute this term here, right? 2 by 3 r square minus y1 square to the power 3 by 2. Let's cancel out few terms. So this 2 and 2 got cancelled out. This whole term will cancel out with this root. So now tau for you will be, tell me guys, please help me, S r square minus y1 square divided by 3. You end up with this formula. And I have missed I. Correct, right? Now, don't worry, you should not learn this formula, not required. So tau for any circular cross section of radius r is given by this formula. Now same thing we'll do. Can you tell me when we are at center what will be the value for y1? 0, right? When we substitute 0 here, we are maximizing quantity because this is negative sign, right? So tau max again is at what? Neutral axis. Now substitute r is y1 is equals to r means you are at the outer fiber. You can be here, you can be here. When you substitute it is what? 0. So same property we are getting for circular section what we were getting for rectangular cross section. That shear stresses are maximum at neutral axis, 0 at the outer fibers, irrespective of cross section. It is either rectangle or either circular, it is 0 at the outer fibers. Alright, now what I'll do is we'll again form the cases and I hope you can directly judge this. Can you tell me how shear stresses vary in circular cross section? Linearly, parabolically, cubically, or any other option remains constant? Because it is y square here, right? y1 square, that means it varies parabolically as following the rectangular section. So again we form two cases at y1 equals to either any r. We should not say plus minus r, we will say r. Then your tau becomes what? 0. At the outer fibers it is 0. When your y1 is 0 means you are at neutral axis. Then your tau becomes tau max, and I hope all of you know the formula. It becomes S r square divided by 3i. Alright, now what I'll do is I'll substitute I value. We know for circular section, solid circular section, I value is pi d4 by 64. Let's substitute this value. I want your help in this, guys. S r square divided by 3 pi d4 by 64. Now what you need to do is write this d as 2r and then raise power 4 to it. Let's do this. So we have tau max is equals to S r square divided by 3. I'm setting this 64 to numerators and this pi as it is. Alright. Now this the d can be written as 2r when you raise power 4 to it. So it becomes 16 r to the power 4. Correct, right? I hope I'm correct. Now this 16 and this 64 got cancelled out. This r square and this r square got cancelled out. And what we end up with? We end up with tau max is equals to S divided by, we have 4 by 3 outside, 4 by 3, and we have pi r square. Correct, right? Can you tell me what is pi r square? Area. What is S? Force. What is force by area? Tau average. So always shear stress acting on cross section is force by area, force by area, force by area was average. Now what we have understood, that tau max, that means that neutral axis is 4 by 3, that is 1.33 times, that is 33% higher than average value. And what was shear stress at the outer fibers with basic approach? Force by area only, right? But what we are getting now? 0. So that was the error. Again, assuming that you understood this part, I am coming to the conclusion part now. And the conclusion part is this. Let's draw the distribution. So this is your cross section length, this is your neutral axis. We know at neutral axis our stresses will be 4 by 3, that is 1.33 times 4 by 3 times of tau average. Alright, and at the outer fibers it is 0, and we know it varies how? Parabolically. So what is this? This is tau max, this is 0, this is 0. And if we don't go by this formulation, basic strength of material approach, then everywhere it is what? Tau average. We don't bother about whether we are at neutral axis or out, just average, force by area. Everywhere it is force by area. Now we are saying that is not correct. The actual values are, you're over predicting here and you're under predicting here. Under predicting by 33%. So it is bad. Alright, so I hope you understand. So this formula we need to remember, and let's summarize this. Then I'll go to I section. How to solve generalized cross sections, because you cannot do this derivation in your GATE exam, right? Every time considering a strip, and I section is slightly on the difficult side, and maybe it will be time consuming. So we have rectangular cross section, we have circular cross section. I just want you to understand few things. Tell me what is the formula of calculating tau max for this. Tau max for this will be, tell me guys, 50% higher than tau average. Correct, right? For this, tau max will be 33% higher than tau average. Tau average is always force by area. So if it is rectangular, length into breadth. If it is circle, pi r square. Whatever may be the cross section is, your tau max will happen where? At neutral axis. This is common for both. Correct, right? Now, whatever may be the cases, your tau is 0 at what? Outer fibers. What do you mean by outer fibers? When you have a rectangular section, outer boundary. When you have circular section, everywhere on the outer boundary you have this as 0. It is same for circular section also. Tell me the next important property of shear stresses in any of the cross section. Yes, it is what? Parabolic behavior. With 0 at the outer fibers and maximum at the neutral axis. I hope you are in a good position to calculate tau max and you understood why we are doing this. The only thing in your exams is you should know what shear stress is acting, otherwise we need shear force diagram. Alright? Now, I'll do one thing. I'll give you a generalized case where you can solve for any cross section, any location. Need not to be neutral axis, need not to be outer fibers. Anywhere you can just substitute this, whatever method I am going to tell you will help you in solving those numericals. Now what I'll do is I'll tell you the numerical. You need to I'll tell you the numerical and we'll solve it together. Alright, now the numerical is something like this. There is an I section beam on which a load of 100 kilonewton is acting. Alright, how the beam looks like, I'll show you this. So you have an I cross section beam. You have an I cross section beam and the dimensions are something like this. So all dimensions are in mm. Alright, all are in mm. This is 50. This web height is 100. Flange is 10 mm thick and this is also 10 mm thick. Same here, it's symmetric everywhere. Alright, and they have given the coordinate system as x and y. And on this system, there is a shear force S is equals to, I guess it is 100 kilonewton acting. Alright, now the numerical is numerical is what is shear stress acting in MPa, fill in the blank, at the junction of web and flange. Alright, in web. Now this is huge thing. This is very doubtful thing. I'll tell you both the cases. Please try to understand this. Alright. Now I'll go by the method which I recommend you should always use in your GATE exam. If you want to calculate any shear stresses, what is the formula? SAY divided by IB. Just remember this. Alright. Now S is the load acting on the cross section. We know this, 100 into 10 to the power 3 Newton. This is not an issue. I is moment of inertia of this section about x-axis, because all the cases are vertical bending. So I hope you know how to calculate IXX. If not, please go to the previous lecture in which we have seen how to calculate moment of inertia of various cross sections. I am skipping this part in this numerical because I assume that you know this, and if you solve this right, your value will come out to be 3.86 into 10 to the power 6 mm to the power 4. Please clear this if you have doubt in this part. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. 3.86 into 10 to the power 6. So I use known. Now I'll come to A, Y and B and how to solve this numerically in one shot in your exams. Alright. Now tau is equals to. Now whatever be the point at which you want to calculate your stresses, the way is this. Start from top section, alright, and color the zone till the point where you want to calculate stresses. Or start from lower section and color the zone till you want to calculate stresses. So forget about neutral axis, start from outer fiber and wherever you want to calculate your shear stresses, color your section till point. Now what do you mean by this? I want to calculate stresses at this point. Alright, so what I'll do is I'll start from top surface and whatever comes in between I'll color that area. I hope it is clear to everyone. Similarly, it's not a rule that you should come from top, you can come from bottom. But when you start from bottom, right, you will be coloring everything until this point, then you will stop. Alright? So, now the numerical is over. S is 100 into 10 to the power 3. This is clear to everyone. Area is the shaded area starting from top till the point you want to calculate stresses. Can you tell me what we have shaded? We have shaded the above rectangle, right? So it will be 50 into 10. So I'll write 50 into 10. Y is the distance between shaded area CG to the system CG. Now what do you mean by this? When you see the shaded area, it's a rectangle, right? Sorry. Its own CG will be here. Alright? Now the system CG is here. What is the distance between these two? I hope it is clear to everyone how we can calculate this. What is this distance? This total is 100, right? Half of this is 50. And this 10, half of it is 5. So distance between this point to this point is 55. So distance between shaded area CG to system CG is Y, which comes out to be what? 55 in our case, divided by moment of inertia. I have already told you, you can calculate this easily. This is nothing but our IXX in this case, multiplied by, now B is catch. B is the point, or B is the thickness where you are calculating stresses. Now you are calculating at junction, right? Now the junction has one issue. The issue is junction can be on the upper flange section, then the flange thickness becomes 50, and this junction point also carrying web which is having some thickness of 10. What to solve? So in your exams or anywhere, the numerical can only be framed in such a way that please calculate shear stresses at junction in web. Please calculate shear stresses at junction in flange. They cannot calculate shear stresses in junction if it is a combination of two different thicknesses. So wherever you want to calculate, right, that thickness should come here. So let's say for example, we are calculating in web center portion. So web thickness at this junction is 10, right? So 10 will come here. That's it. Once you solve this, it comes out to be tau is equals to what solution I am having. You please can verify this, 71.1 MPa. So this is the shear stress acting at the junction in web. If you want to calculate in French, what you should do? Same SAY divided by I, but B becomes what now? Your flange thickness, which is what? 50. So divided by a bigger number. I hope you can assume this, or you can imagine this in your mind. So this is the way of calculating using a formula SAY divided by IB. And I'll be proving one more thing with this. Now this is for your homework. I want you to do this. In this cross section, I have moved from top till this point, right? Now you want to calculate stresses. What you'll do is, you'll start from bottom, color this entire zone and reach here. So what will be your shaded area? Your shaded area will be this. Correct, right? Now this S remains same. Write your area. This area plus this area. Makes sense. Then this Y is a catchy part. Now Y is the distance between your shaded area CG to the system CG. So your shaded area is only this inverted T now. Correct, right? So what you need to do is additional work. You need to calculate its CG. Let's say it lies somewhat here. Your system CG is here. You need to calculate this distance, substitute here. Repeat the same procedure. Your value should come out to be what? 71.7 MPa. Please try out this exercise. This will make you comfortable with this shortcut method. In your exams, we should always take a call in which we can skip more calculations. For example, if I would have shaded the lower portion till this point, right? I have an additional work of calculating CG. But if I move from up point till this point, I know it is a rectangle, area is simple, length into breadth, and CG is exactly at the center. So this call we need to take in your exams. That should I move from top surface or should I move from bottom surface? At practice level, we have moved from top. Please try out same numerical, move from bottom surface. You need to calculate CG. Refer previous lecture if you have issue in calculating CG of any arbitrary cross section. Once you know this, substitute these values and you should get 71.1 MPa. Whatever procedure you follow, in the end, the solution comes out to be same. I hope this is clear to everyone. Just for your completeness, just for the completeness, I'm telling you the distribution. If you see I section, right, you must have seen this before. Can you tell me what shear stresses you expect in the outer fibers? 0. And what you expect at the neutral axis? It should be maximum. That's what our theory says. So when you move, right, and always it is parabolic. So when you move, it is something like this. So you have reached here. Correct, right? So you have started with 0. You are having some value of shear stresses. You can calculate, it comes out to be some 71.1 divided by 5. You can calculate this in flange. You have calculated in web. Then what happened in web? It suddenly shoots up. Yes. Why? Because see, same shaded area, but the difference is divided by B. If you are calculating in web, it is divided by 10. If you are calculating in fetch, it is divided by 50. So it is 5 times lower actually. And after this, if you move in web, right, we know it is in parabolic, maximum here, then it comes out to be like this, then it becomes like this, and it is becoming like this. So this is how your shear stress distribution looks like for an I section beam, which is subjected to a load of 100 kilonewton and magnitude we have calculated. I hope this is clear. If you have any doubt in any of the topics we have discussed today, please let me know. We can have an additional lecture prepared, and definitely we have a separate lecture for solving all the numericals related to shear stresses. So maybe I'll combine that with shear force and bending moment diagrams also. So it's like, first you see a beam, calculate a shear force, and then calculate shear stresses corresponding to it, and complete formulation of a beam. Alright, just to end up this lecture, I just want to prove one point. Alright, and then point is this. Just a proving point, not required actually. We have already done this. You have a rectangular section of width D and depth H. Correct, right? This is your neutral axis, center point. Now what is the formula? Tau is equals to SAY divided by IB. Correct, right? Let's use this formula. Now suppose you want to calculate stresses at the outer fiber. Correct, right? Now what I have told you, wherever you want to calculate stresses, start from top surface and go till that point. Alright? Now where you want to calculate stresses? On top surface. Where you want to start with? On top surface. So what area you will be coloring? 0. Correct, right? So this area becomes 0. So what stress we have on the top surface? 0. Correct, right? Now let's suppose we have started with bottom surface. So S as it is, area, start from bottom surface. Where you want to calculate stresses on the top surface. What you color? The entire rectangle. So area becomes B into H. But what is this Y? It is distance between the shaded area and the system CG. Now shaded area is whole rectangle, system CG is whole rectangle. Can I say both are the same? So what is the difference between these two? 0. So what is stress in the outer fiber? 0. Similarly, what is stress in the outer fiber at the lower part? 0. Now suppose you want to calculate maximum shear stress. The procedure is this. Start from outer fiber. Alright. Color your zone where you want to calculate stresses. I want to calculate stresses at neutral axis, max. So I'll start from outer fiber, I'll move and I'll color the entire zone till that neutral axis. Now I'll apply this formula. The formula is S, area of shaded area. So this B into H by 2. Y is the distance between shaded area CG to the system CG. Now shaded area CG, rectangle will be this. Your system CG is this. What is the distance between these two? So this is H by 2, right? Half of it will be H by 4. So I'll substitute H as H by 4 divided by I, we know B H cube by 12 into B for rectangle, wherever you go it remains B only. Once you solve this, right, you will get this as 3 by 2 S divided by B into H. What do you mean by this? Tau max is 3 by 2 times of tau average. So another way of proving the same thing. Initially we have used an integration method. Now I am using a generalized method. So just to summarize, I am again repeating this. Shear stresses in bending are parabolic in behavior. It varies parabolically in cross sections. It is maximum at neutral axis. It is 0 at the outer fibers. Whether it is rectangular cross section, circular cross section, I, Z, C, you can try out any numerical. In rectangular cross sections, your maximum shear stress is 3 by 2 times of tau average. Tau average is always force by area. Similarly, for circular cross section, your shear stresses are 4 by 3 times of tau average, that is 33% higher. All varies parabolically. And we have seen a shortcut method which is known as SAY divided by IB, where A is the area of shaded zone, Y is the distance between shaded area CG to system CG, I is moment of inertia of bending, which is usually x-axis, IXX for us, and B is the thickness where you want to calculate stresses. How to shade this area? Either start from top of your cross section or start from bottom of your cross section, and wherever you want to calculate stresses, just go there and color that zone. For example, if for let's say you can try out this, guys. I'll give you an I section. Let's say same dimension, 50. We have already solved this, right? This was 100, this is 10, this thickness is 10, and this is 10. Alright, now what you can do is, you can calculate tau max for this. So now you cannot apply this formula 3 by 2 tau average because it is only defined for rectangle, 4 by 3 was only defined for circular, for I we have an issue. So what you should do, we know maximum will happen at neutral axis. So I need stresses at this location. What you will do, you either start from top surface or you start from bottom surface. It is same in this case. I'll start from top surface and I'll color the zone till the point I want to calculate stresses. Now you have this T, right? So area is known, S is known, area is known, I is known, B is thickness where you are calculating stresses in web, right? So this becomes 10. So it's clear to everyone. Now the issue is Y. Now what is Y? Distance between shaded area CG. Shaded area is this T. So if you see its CG, let's say for example, will lie somewhat here. Your system CG is whole, right? It will lie here. Just calculate this Y bar and substitute in this and your numerical is over. Alright, try out this. If you have any doubt, you can post your doubt in group or post in the portal itself, or we'll talk in WhatsApp. Sorry for this interruption. And we can discuss all these quantities. Try out these numericals, verify your solution what we have seen before. Alright, and I'll be posting the next lecture for numericals on this. Alright guys, thank you.